And, uh, yeah, we're very happy to have Ronna from CMI, who is visiting, has been visiting for since last week. He will give a board talk on Tuesday.
Yes. So, yeah, thank you. I was asked to talk about Zoo-recursion relation. So, it is Zoo-recursion relation allows us to compute torus endpoint function recursively. It's a mathematical construction. So, my plan is to derive uh, the simplest possible case of Zoo-recursion relation, and I want to talk about how this formalism is helpful in order to compute certain things in 2D CFTs, and how we can construct certain things in integral systems. Right? As I've said, that it's a formalism to compute endpoint function in on a torus, and this is a quite very it's a very old thing. As you can see that this is Zoo's PhD thesis on vertex operator algebras and recursion relations. So after that, this thing has been modified a bit. So the first modification came from Hartman. Is it visible? Team. So this is the slight modification of the original recursion relation, and then the most general case that we know is the very recent paper by Kepler done 24, and all of these recursion relations are on torus, but there are version of Zoo recursion relation in different topologies. So if one is interested, then one can check with this paper. Many collaborators where I think effectively they have written a Zoo recursion relation in arbitrary genus random surfaces. And so this is obviously a very hard paper to read. If you want to find a very simple paper where they have for a review, then this is a readable paper for me. Another one is Melanie. 2018, and I think we also did a quite good job to write a review. So there's a paper by us where we actually review this recursion. So before I go into the details of recursion relation, I want to give some introduction. So let's see. So my conventions are that if I write z, then this is a coordinate in plane, and if I write u or v, small v, so that's a coordinate or cylinder. Okay. And what many people have done is that they have written torus, a field in plane and a field in torus, but they always write it in this fashion. But it's a bit of abuse of notation. So I will try to keep things understandable. But sometimes if I just do the mistake, please tell me. Don't understand. So
The identification is the torus.
So z is the coordinate in plane, and then this is like e to the power u.
So that you write x plus tau y, then it is.
Yes. Yeah. So I'm working in 2D CFT with only chiral half. So I have a 2D chiral CFT. So it is well established that if you have a 2D CFT, with only one chiral field present, that is your energy momentum tensor, and I'm writing U because this is the energy momentum tensor on a cylinder, then it is well known that the CFT will have infinitely many conserved charges which are in involution with each other. They are known as the KdV charges. So I am writing the first few KdV charges. So, so charges are, let's say if you have the NH charge, then that is the zero mode of the current, which has a weight of n+1, and the zero mode of the current. Now I'll list first few currents which are known. So let's say the first current is obviously J2, which is your Hamiltonian, which is T U, and then zero mode of that, which is nothing but L0 minus C by 24, where C is your central charge. And then J3 is 0, J4 is P of U2, where this bracket means that I have normal ordered this one. I'll just write the definition of normal ordering in a bit, and then zero mode of this. And you can do this integral and find the mode expansion of Pt0. I'm not writing it, it's complicated. And then J5 is again 0, and J6 is
So I think I missed something at the start because I was here a little late. What are you doing and why are you doing?
okay. So I was asked to talk about zoo recursion relation. So it is a formalism where if you have an endpoint torus function, torus correlator, zoo recursion relation tells us that how to compute that endpoint function recursively. By recursively, I mean that you can write the endpoint function as a sum of n-1 point function, and then you do it recursively and you find endpoint function. Right? As an application, what I want to show is how there are a few applications that I want to talk about. One is how do I fix. So I was talking about KdV currents, but there is no until Maloney's work, there was no systematic way to construct these currents. So I want to talk about how to construct KdV currents as an application of zoo recursion. Then I want to talk about how to construct something called Boussinesq currents. I'll talk about this. And then I want to talk about GGE and its modular transformation. This is my plan to talk.
Why are you doing this?
That I will tell in, let's say, 10 minutes.
Okay. I mean, just to give an idea. I mean, so
Giving you an idea that's
what's the problem that you want to address?
exactly. So the problem was to understand the modular properties of a generalized Gibbs ensemble when you have a conformal field theory with some W3 smooth.
Why?
Yeah. The next question is why.
Yes.
So the reason behind is that we know from ADS-CFT correspondence that if you have a gravity theory in ADS theory with some SL3R cross SL3R gauge group, such as Chern-Simons theory, the dual theory has a dual theory is a conformal field theory with W3 plus W3 smooth. Now the point is that people have computed from the gravity side that you have a higher spin black hole, they have computed entropy and stuff like that. But from the CFT side, because W3 algebra is very difficult to navigate, the model, even the characters of W3 algebra was not known. Even I mean, it was very recently people have found it. Like, say,
Isn't this Rajesh and Matthias in 2000?
Yeah, similar. Yeah, yes,
something like that.
Yes.
Yeah.
Then this paper, Hartmann and Gavard.
Yeah, but that's afterwards.
Afterwards, yeah. So the point is that they also said that they don't know how to compute the modular transformation of the GGE.
Yeah.
So from the CFT side, you cannot verify whether the gravity results are correct or not.
Why? What? I'm going to ask some kind of questions.
Okay.
Why am I interested in spin black holes?
I mean, Yeah, interesting as in sense like it's just a mathematical formalism.
No,
to know
sure,
about.
but is there a larger goal in mind? I mean, you're doing it for something. Do you have a question in mind?
Uh, uh, for me, I never actually looked at the gravity side theory. I wanted to learn the CFT side because this is a very mathematically this is a very interesting question to understand the modular transformation property of the
Sure.
characters, etc. And there are some motivation to understand this in the context of eigenstate thermalization hypothesis and all. But
Spin threes, where do they, I mean, occur in this case? Do you have any sort of real system in mind?
I right now I don't have much idea about this, but yeah. But I think he knows.
Yeah, I mean, I'm probably notorious for asking this question.
No, no, it's
Why are you doing it? But okay, yeah, sure.
Yeah. So yeah, so basically, just to summarize that, I wanted to understand the modular transformation property of the generalized difference symbol with W3 symmetry algebra, and we have some answers to this question. And this construction of KdV charges and the Boussinesq charges actually helped us to understand this. So this is how this is gonna work out. But I have talked so much, but I have not told you what is Boussinesq. So sorry. Yeah. So this and then this. Visible. So this is a. So I will in this talk I will show you an example where I will tell you how to construct this current exactly.
Yeah, I have a question.
Yeah.
I'm not familiar with this, so can you maybe understand that why J5 and 0?
Sorry. Oh, I see. Yeah. So the reason behind this is follows. One thing is that the very hard answer is this: that if you have an integrable system, you can always write some Young-Bastard equation, and then you can solve the spectrum, and you can see that the spectrum is zero. But the simplest answer is that. So we know that energy momentum tensor has a conformal dimension 2, and the next current should have a conformal dimension 3, right? So the simplest possible field that you can construct from energy momentum tensor, which has a conformal dimension 3, is T prime, which is a total derivative. That's why it's similarly, if you go to J5, you will see that the only things you can construct out of energy momentum tensor are total. Sorry?
Boundary conditions is equal to.
No, it's just that the charge is 0. If you have T prime, the 0 mode is 0. The 0 mode of this, so if you have T, then you can mode expand. And then for T prime, you can show that the 0 mode of this of the field is 0. That's why the charge is. Yeah, thank you. Okay, so this KdV system has been studied by BLZ and so on, 4-5 papers, and where we know the spectrum of discharges, we know eigenvalues of the charges on the highest state, on the first excited state, on the second excited state, and so on. And then also people like Dore, Dunning, Tateo, Negro, etc. from 14. So they have also developed certain technology called ODIM correspondence to solve the spectrum of the problem. But we still didn't know how to construct this currents rigorously. There are a few reasons of that. So first of all, if I ask you to construct the next charge, which is not known, I have not written here. Though, so the first intuition that one should have is that I will write the most general ansatz of the charge, and then since these charges commute with each other, I demand that they commute with all other lower order charges, which we know, let's say, and I can fix the undetermined coefficients in this, right? But if you try to do this, and if you try to do this for example, if you try to show that J2 and J6 commute with each other, it will be very difficult, because when you try to write a zero mode of T composite object, it will be a huge mess of Virasoro. And then if you try to commute these things, it will be very difficult to show that it's zero. So in this way, constructing the charges are very difficult. Understand? Sorry. So what Meloni et al. Did is the following. So instead of focusing on the charges, they focused on the currents. So they write the most general ansatz of the current they want to fix. So let's say J2M. And I know from the weight I can construct this. The first term will be some t to the power n with normal ordering plus some derivatives of t prime, blah blah blah. So it's a huge mess of linear complex. So for example, if I want to write J8, I will write T, normal ordering, then some coefficient. I will write T prime, T, sorry, not T prime, T double prime, T, and all other combination that gives me J8, right? And then what they do is compute their thermal correlators, right? And when I say thermal correlator of an object, let's say an operator O, so this is like this is the thermal correlator. Like this. Place over the model. So since we have only energy momentum tensor present, this will be some Virasoro model. And I will argue that using zoo recursion relation, you can compute this thermal correlators. Then you perform the normal ordering and you get some result. Okay. So you compute the thermal correlator exactly, whatever plus alpha, some beta, dot. And because we know the spectrum of the charges exactly, we can compute the charge. I will tell this properly. I'm just giving you an idea what I'm trying to do. So on the highest weight state, which is 0 H, this we know due to the work of DSZ. And the argument is that since this is a trace of J q to the power is 0 plus C by 24. So the argument is as q tends to 0, when I divide this by q to the power h by C by 24 and take q tends to 0 limit, this should match with the charge on the highest weight state, and I can fix the undetermined coefficient. This is what Meloni did. So yeah, so I will explicitly tell you how to actually get this without how to fix this constant using zoo recursion. That's my plan.
Sorry, that's some basic questions. So even the statement is that in any 2D CFT is either you should have this KDB charge.
Yes. No, the statement is that if you have a 2D CFT with only energy momentum tensor as your chiral field, if you have only Virasoro, then you have KDB. Now I will give you an example where you will not have KDB, you have something else.
No, even before coming to that,
Yeah.
even with the setup, I just want to.
Yeah, sure.
So the statement is, I mean, the question that is coming to my mind is why I'm suddenly looking at KDB charges.
Okay.
So the KDB charges will be there if I have a 2D CFT chiral sector and only stress tensor.
Only stress tensor.
So then I should have this.
Yes,
things,
yes.
and then I want to compute.
Yeah.
And then that's the first.
Yeah.
And then you are looking at thermal 2-point function.
Yes.
And hence torus
Yes.
correlated.
Yes.
But what is the story in this? So the problem of finding J6, J8, knowing J2, J4, why can't I do it? Or is there any abstraction of looking at sphere partition? Sphere. Why are you looking at?
Oh, so
I
you-
mean, I don't know.
Yeah, you're saying that maybe in plane, why do we not study KDV charge?
Is there any obstruction?
Yeah, no,
why
there
am I
is-
looking at certain
No,
things?
there is no obstruction in the plane. You can actually construct KDV charges.
But then that will not that give me J?
Yes, but that will be different than this because quasi-primary is not necessary. So I have not told you that all the currents are actually quasi-primaries. It's not primary, and quasi-primaries does not transform in a nice way when you go from plane to cylinder. So it will have some additional pieces. So essentially the construction is more challenging in a cylinder than plane. So the reason we want to study these things in cylinder because we want to study something like this, where knowing the charges in cylinder manifestly comes here. So that's why. So I think it will become more clearer if I get 5 more minutes.
And then there is another probably. So this equation is the right hand side is the state, left hand side there is a number.
Which one? Sorry.
This equation.
This equation. This is a number times an alpha.
This is a number on a state.
This is an operator acting on a state. So I get the eigenvalue. So let's say this is eigenvalue, and this is a state.
And the left hand side is
Left hand
specifically a number.
No, this left hand side, I'll tell you why. I mean, sorry, yeah, maybe I should not. No, maybe I should have written the eigenvalue should match with this. Sorry, this is not. Sorry. Yeah. So the next simplest question that one, so the next
So
simplest,
this last one was what you wanted to take the limit of q goes to 0.
yes.
Why does I mean why do I see that?
Okay.
How
So
do I see that?
trace
It's
of in q to the power n0 minus c by 2. Let's say I can compute this using two recursion. Let us assume. Okay. So what does that mean? This is a trace is taken over Virasor 1. So the first term is h, then you have L minus 1 h.
yeah, sure.
Third term, right?
Yeah.
So if I just expand this,
Yeah.
you get q on h is just q to the power h q to the power h minus 2 by 24, right? And then you should get h.
Yeah.
The other terms, this acting on this will pick up a factor because this is the result,
Yes.
right? So I should get L0.
So you're gonna get more things from him.
Exactly. So the thermal correlator actually have the information of all eigenvalues of the charge.
Yes.
But now if I
This is how for the fall off.
yes, this I have a follow-up if q tends to 0. So if you divide and then q takes to 0 limit,
I see. Okay.
this part is
So
zero.
that's sort of like
Yeah.
an identity.
So the next simplest question you can ask is that what if I don't take Virasoro, but I take some other symmetry algebra such as W3 algebra. I will tell you what the W3 algebra is. So do I have this kind of construction where I have infinitely many charges? And the answer is yes. And those are called the business charges. So I need something. So instead of writing the algebra, I'm just writing the OP because that will be helpful in the later cases. So W3 OP, let's say. Now you have two things. You have an energy momentum pressure, which is spin 2, and you have a WP, which is spin 3, which has a conformal dimension 3. Now the OP is E U1 E U2 is by 2 of you have 4. I I don't think I should write all.
No, you really shouldn't write down that.
I will just write the important term, which is the second order pole, which is
Yes.
pole.
It's a weird thing, right? There's a one over C minus 22 by 5 or something.
Yes, yes. So B is equals
Yeah,
to
B is that.
Yeah.
No, B is not that, B is something else.
no B is that 16 by
16, yeah, by
B square
5 plus some 5.
Yeah.
Yeah, yes. I remember this.
So it's a horrible looking thing,
Yeah.
and this lambda is TT normal order. Yeah. So far so good. So now I'll just give you the first two known charges of the quantum Bhutanist hierarchy. So the Bhutanist charge is the first charge is 0 mole of T. The second charge is 0 mode of W, and the third charge is 0. The fourth charge is W. And there is a fifth charge. I'm not writing, I'll do it. Hopefully.
I3 is 0.
I3 is 0.
Any quick way to see that?
Yes. So again, the same thing I can say that either you solve the spectrum
Of course. Yeah.
and then you see that this is 0.
Yeah.
Other way is that here it is tricky. What Subrato asked last time is that I can always say I3 is basically you have a current which has a weight 4.
Yeah.
But there you could construct a thing which is like TT. But this does not appear. So the reason is that if you actually solve and find the eigenvalue, then you'll see that this is 0. Also, another way to see that is that if you derive the classical charges of the Bhutanist hierarchy, there also it is 0.
Yeah, but these are not very easy to see, of course. Right?
Yeah.
Question was it easy to see?
It's not a
But okay.
Okay, now I think I have partially answered why I want to look into the charges, but so reason to study the charges of either KDB or Bhutanist is that we want to understand something called a generalized Gibson symbol. Now, since you have many conserved quantities, you should write a partition function with your, so this is base and this is your usual partition function. But now since I have a conserved charge, So for W3, I have this. I can write some y to the power W0. Now this is the partition function of a W3 CFT because now you have two kartas because L0 and W0 commute with each other. Right?
I had a very long standing thing that I've been asking lots of people, but I didn't get any answer. So this guy has a singularity at the Liang. And if you write down higher W algebras, they also have weird singularities.
Yeah.
Do you have any idea why?
I don't know. I don't know the right answer to this question, but if you this is the reason why we were trying to actually do the TBA for Liang, and it gets very difficult because there is a singularity.
No, the fact that there is a singularity means you have to sort of.
Some
I mean, the algebra will not be the same.
Yeah.
So you have to sort of contract the algebra.
Yeah.
That's something else.
So I think
But
that-
why it has a singularity at the Liang is something that I tried to look in
I also
places that long time back. I have not. I actually asked it. I mean, Alex Nadoni at some point. He also did.
So the way people have tried to do
There are some more weird things as that. I mean, there's some 35/7 and so on and so
If
forth.
you go higher and higher.
Yeah. If you find any answer to that, please let me know.
Okay. So since this is the partition function for a W3 CFT, now you should notice that this is the second Bosnian chart. Now, why I want to study this is the question what Arjuna asked is that this theory is a W3 CFT and the gravity theory is known, which is a Chern-Simons theory with the gauge group SL3R cross SL3R. And I want I mean, it's an interesting question to understand the boundary state. But since the W3 algebra is very complicated, I think I have established that fact. This computation exactly is not true. So also, if you want to understand the high temperature behavior, you should understand the modular transformation of this object, which was not. So, but you can stop me here and ask me that why I am looking at the charges if you want to compute the partition function or the modular transformation of the partition function. So the answer is the following. So what people have done, Max, Browning, I think I'm spelling Browning, Gerard Watts, and Karimi. What they have done is the following. Instead of W3, let's ask this question with a KDV charge. Right? So you have a partition function with KDV charge. So let's say I3, which is a KDV. Right? Now this y is e to the power 2 pi I some alpha, where alpha is your chemical potential. Now what I can do, I can take small alpha and expand this. I will get trace of q to the power something like this. Right? And now, since you know I3, you compute the thermal correlators of these objects, individual objects, for every value of n. Then you take the modular transformation. And then you ask this question whether you can sum it back or not. And the answer is yes. So they have done it for a specific theory, field fermion and Liang. But I think if I have time, I'll show that this is generally possible. Now, so, and this thermal correlators you can compute using two representations. And then what they have shown is very interesting is that if you take I3 to the power n, compute thermal correlator and take the modular transformation, you will get some tau to the power 2n factor times I3n. So after taking the modular transformation of I3 to the power n, you should get a tau to the power 2n. It's a modular object. Well, not modular, quasi-modular object. So but you will get other terms. And it turns out that you can write these objects in terms of lower order, other KDV charges and all the quasi-primaries of the KDV have. That was the clue. And using this clue, we actually did this, not this one, but this one. So here we actually expanded.
This modular transformation check is to make sure that the partition function is correct.
Yes. No, but also like we don't know the modular transformation problem. So the whatever it coming out, it is the modular transformation. We don't know the. I will show you what is the result. So using this trick, we actually do this, where we again take small alpha and expand this and take modular transformation of this object, and what we get is so z at 1 over tau is equals to trace of 2 to the power 0. Now let's see by 24, and then you have e to the power some alpha, phi I alpha, and some w hat, and the 0. This w hat is
Why you said alpha is also
Yeah, there'll be some.
there is
there is
a
a sorry. We don't write it in terms of alpha prime, but you can write it in 2 pi I alpha tau 2. And then w hat is series
So there is this, please, write down what you have to write down. Then,
just follow that. Then what you get is I have to explain what this is.
yeah, so I want one quick thing to ask you. You also explain this.
Yeah.
So a while back when we were doing the similar sort of modular transformations for the BMS3 and so on. And then just after that, Hartman, Detorne and Hoffman, they had a way of doing finding out similar things for the warp CFDs. So there is a way that you can think about trying to exchange the two circles in order to get what the modular invariance, at least the S transformation would be.
Yes.
Did you guys also try to do something like that?
So we know that you have a torus endpoint function under modular transformation, how that behaves.
No. What I'm saying is that you would be, so this is in terms of the, vacuum basically. So you can actually, there is a trick that these guys write down in 2012, I guess. So it's Hartman, it's Hoffman. Letorni, Letorni, Hoffman, and Hartman. So you can use that for any sort of symmetry algebra, and it boils down to the fact that you have an thermal circle and you have another one. So it's just the exchange of the two S1s in some sense.
Yeah. That's true.
So if you invoke that, and they have an argument where they use the charges in the vacuum, and then you can get what the S transformation would be like.
But
So-
here the modular transformation
Yeah.
does not depend on what representation you are doing. It's in principle when I write this modular transformation. So here the trace is taken over some representation of
No, that is fine. Yeah,
But it does not depend on the which.
Oh, sure. So it's the same thing there. Yeah.
Okay, I have not.
It's two. Exchange of the two circles.
So I have to check.
Yeah.
This is
So
like a
that's-
defect space in the description. What do you think about the, after you do the model transformation, what do you?
So you write this down in terms of the vacuum charges. And then if you, since you are on a P2, so you would be able to exchange the S1s basically.
Right.
And then they have a trick to actually find out what the S transform version of this is. So I can show you the references. 2012. Letorne, Hoffman, and Hartman. And you can use the same thing for our stuff as well. So, the VMS30 formula can also be rewritten in that way.
So here, the square brackets mean that you are computing the OPE between. Okay, let me just write few terms, then I can. So let's say I want to compute. I want to write n equals to 1. So that is just, which is W. Now if I write n equals to 2, this is WW. And this bracket means that you take the OP of this two field, and this two means that only the coefficient of the second order constant. So the modular after taking modular transformation, this field, this W hat can be written in terms of the coefficient of various fields taking OP and only the second order pole terms. And when I do recursion and try to do the modular transformation, you will see that this comes naturally. Although this is a conjecture, we have not proved it. I'm trying to prove it now. Another thing that we kind of think is that if you instead of W, if you had any quasi-primary and then sitting here, that means any KdV or any Buzanist charge for that matter, this similar structure should hold. That's an again, this is like a guess from us, but we have not proved it.
Why would those things be interesting? This one is the partition function.
Yeah, but then you can because ultimately if you can understand, if you add all the charges, in principle you should, if you write a GGE, you should write all the charges. Yeah, and then Dimarsky et al. They have found so for KdV charges, when you have all the charges, they have found the dual gravity theory, which is this KdV charge black hole paper, and it is not a priori. We cannot say that whether similar kind of dual theory should exist for Buzanist or not. It's non-trivial, but something that I want to do.
But you want to do it for the W3.
Yes, I want to find out this thing.
Yeah, if you are doing it for the W3, you do not need. At least if you're thinking of the SL3R, then
I don't
you
need
don't need the rest of it.
No, but I want to know if I add all the charges.
Yeah, so you're saying the W3 analog what of the
Yeah.
KDB.
Is there is it equivalent?
I see.
Yeah.
Yeah.
This alpha value comes from the original vector problem.
Yes. Yes.
You made a strong statement that this will be for any person.
That's what I think. I think hopefully I can prove it in a few months and then
Quasi-primaries as in
any currents of KDB or any currents of Buzanix, if you instead of writing W3,
that's a pretty strong statement.
it's a strong statement, I know, but I have some proof that it is kind of coming out to be true, but I have to prove it.
What are those objects in the sense that trace of Q to the, I mean, so partition function with, I mean, exponential of.
Some, let's say, right here. So
Why is that an interesting object? So you're saying the GD will
should have all the charges.
quasi-prime?
Currents are quasi-prime.
Yes.
Yeah.
So the charges
Charges are
generated
the-
by
Yeah.
generated by the quasi-prime.
Yes. So in principle, for every level, if you can construct the quasi-primaries, you can always write the charges as a linear combination of quasi-primaries. So quasi-primaries are the basis.
So let me just ask you, so if you think of let's say I'm looking at just a CFT and I do not have any extra stuff.
Yes.
So if I partition function is something that I of course need and love and so on and so forth. But just from the point of view of the CFT, what are these other, I mean, other objects in some sense?
What do you mean by other objects?
I mean, if you look at quasi-primary and plug that in
Yes.
into something which is like a Z prime,
Yeah.
what does that Z prime do for?
Oh, okay. So basically, when I'm inserting the quasi-primaries, there are also conserved currents, right?
Yeah.
So in principle, when you have
So you're going to another ensemble?
yeah, it's like it's a grand canonical ensemble.
Yeah.
Partition function there.
And you expect that the answers that I get are what's the ensemble input into, so what's the observable which will not be the same substance?
I would assume that if you have a partition function of that sort, and then you can in principle do the model construction, the density of states, and I think I would assume that the entropy that you can compute should be different.
Yeah, it should be different, but it also should be related by the
Yeah, but
change of ensemble in some
Yeah.
sense, right?
yeah,
That's something that you should be able to track as well.
Yeah.
It's good to have one example to see the concept.
hopefully.
One example is tension rescue. So that is something where
Yeah, so that's Rajesh's version.
Yeah.
Yeah.
But I think hopefully in few months we will have the
WL.
yes.
So
Okay, yeah.
and you have to average over the GG partition to retrieve the string partition.
But for WN, if you take large central charge, it's simple. Become very simple. No, I mean not simple.
No, so there the CFT is this symmetric orbital.
Yes.
Yeah.
That you study in the GG. And then you average over all GG, then you get the string partition.
Yeah, just to also throw standard in the works with SL3 gravity is not a good, it's not a good theory, by the way. So it's a very bad theory. So in order to get something which makes more sense, you have to go more to this, HS lambda like stuff.
Okay.
Which is the thing that gives you the higher spin stuff that has been done. The SL3 by itself is actually pretty bad.
Yeah, so I don't know much about the gravity side. I am trying to learn and
So, but yeah, it's It's hard to do this, of course.
So this is the result. I don't think I will have time to do all these things. I will just do the zoo recursion relation now. So this is with next. Yes, you write this. Yes. So now Santanu can wake up. This is something that you could learn.
We should have you here more often, you know. I have to wake up the audience. I'm glad you did that.
Okay, so I have told you many things in the introduction, and now I try to do zoo recursion. So what is so it's as I've said many times, it's a way to compute endpoint endpoint torus correlators. So let us define what is that. So trace over some algebra, let's say, and then I have some fields. So I should write A1, that one, A, N. So this is my endpoint torus correlator. That yeah. So now what I want to do, this is
the variables?
oh, so these are the states. So I'm writing in the vertex operator language. So A1s are the states and the V's are the vertex operator. So the first thing I will do is to take this vertex operators, individual vertex operator, which are the cylinder, and do a conformal transformation and bring it down to a plane vertex operator. But depending upon conventions, I'm just writing this up. It is up to an overall factor z to the power h1, z to the power h2, hn. Because I'm taking all the fields that is on the cylinder, I'm doing a conformal transformation which will give me this small factor. There is a product here, and then I get okay. So when I write this, I should have written BT or something like this, but it's understandable that this is something that is in plane. And then what I will do is that I will, since this is in plane, I can do plane mode expansion. So I will take the first field, I will do this. So I will write V1, V1, Z1, and I will write this as sum A1, A, Z1 minus N minus H1. Sorry, I made a mistake somewhere. This should be K. Right? Only the first field I'm taking the mode expansion. So now this now when I put it back here, I will have there is a sum over k on users. So now I put it back here, and then I write it in two ways. The zero mode, I keep it here, and the other rest of the mode, I write it in a separate. So this one is placed was A10, then you have the A2, Z2 dot, and then you have some overall factors here which are there, and then you have plus again the overall factors. I'm not being careful with the factors, and in the when I try to write it everything compact in the compactor and see. So the next term is there is a sum over k, and then you have k okay. So I've distributed this sum. I have written only the zero mode and the rest of the modes here, and there are overall factors here. Okay. Now what I want to do is I will take this mode here, this mode, I will commute it through all the fields. So I will get all the commutators, and this object will reach at the end when I will have BAN ZN, and there will be a q to the power 0 minus y. So I will commute this field with every object, and then I will come back here, and when I commute this through, I will have a q to the power n.
What happened to your Z1?
Oh, it is there.
Where? Oh, that's the thing.
You commute on the way and then what?
I will commute all the way. This A will come here, and then when this hits this, I will get a q to the power n. Right? And or k here. Wait. So let me write it one nicer way. So I'm calling this term, the second term is as t. Okay. So t, which is the second term, which is not this term, zero mode term, I have kept aside. T is Z1 minus k, and then I have other terms Z2 H2 dot Zn Hn, and then there is a sum over j that is equals to 2 to n, and I'm writing this as trace E into F2 dot. Okay.
So that's a very complicated thing to do, right? Because there is, I mean, everything is going to sort of have non-trivial permutations, right?
Yes, but then you will see why this is interesting after a few more steps. Okay,
So this is the one, this is the jth one in between.
here, so I'm taking this mode, commuting through all the fields, right?
Yeah, I mean, you're just schematically just, I mean, just written.
Yes. Plus, you'll have another term because you have arrived here, and then you should have a q to the power k, and then the total thing. Because then you can, when you are here, you can bring it back using the trace property. You get
Yeah, right. But it's all of these terms.
exactly. Okay, and then obviously this is for one particular mode. You have also a sum over k, of course. So now then I can write t as 1 minus.
So this T also has a level K.
Yes, in principle has.
Okay.
I should write. Yeah, sorry. Thank you. Yeah. All the other terms? Yeah. Plus all these things. Okay. Now I'll use an identity without proving because time. So I'll write this commutator between some random field. This is sum over n's infinity. What is the identity?
That's not too horrible. That's actually fine.
Okay. You.
Insert. We did as a W3 algebra.
Okay. So if anyone wants a proof of this, gamma dual introduction to CFD. Okay. So now after substituting this guy with this guy and do some manipulation, I get TK as you can write it as 1 minus q to the power k. Now you have two sums. That is Weierstrass. But the one love this. So, okay. Now the answer to your question that I have too many sums, but I should get something nice. So I will introduce something nice. Okay. I introduce something called square modes. can think about square modes as your modes in cylinder. So for example, for V of let's say A U, which is a vertex operator on cylinder, the square modes are defined as N U to the power minus N, because you are in cylinder, you don't have weight. And there's a very nice way to compute this square modes. One is basically you write plane modes, right? Z as e to the power u, take expansion and can find this. There's a nice formula that one can use where the square modes of any algebra can find inch of A, E, this where the coefficients are given by log of 10 the power s to A internal equals to s. So if you expand this side and collect coefficient of z to the power j, you will get Cj's, which are this C. Now, very interestingly, if you have a square mode of some field, right, acting on some other field, let's say B. So since if you know the OP between these two objects and cylinder, you can actually compute what is this without going into all the details. In our paper, we actually computed square modes in terms of plane modes and then acted on the objects, and it's very complicated. But if you know the OPs, this is actually this action gives you the coefficient of. So if you have ABOP, and then let's say you have U1 minus U2 to the power n plus 1, this coefficient is this. And you can prove it from here.
What are the C's?
Huh?
C's, coefficients.
Oh, this C's. So this is like the square modes, which are the modes in cylinder, but the square modes can be written in terms of plane modes. These are the plane modes, and these coefficients are those coefficients which can be computed using this expansion. Or you can be very smart and you write V of Az, then use you have plane modes hk minus a or h minus a, and then you know that z is e to the power w. This you do conformal solution, you expand this, and you can also compute this. So, now using square modes, this becomes very simple. Well, not practically, but
Because anyway you want to write
exactly.
on the back on the ceiling.
Yes, ultimately I will whatever the factors outside I'll observe, and after that I'll have everything in cylinder. So, sorry, you had a question.
I have a question, but what was the introduction to the question?
I will take you 2 minutes. Yes, almost there. So after introducing square modes, and there are some simple algebraic tricks that one can use. I am not writing it here. One can write Tk as well, in this 1 by K and sum over j equals to 2 to n m 0 to infinity 2 pi I n plus 1 a to the power n, that is distributive. Then you have Zj and Z1, k, and then you have your n minus 1 point function. That is trace. And then you have the k corresponding to that square mode. So this is A1M acting on V of AJ. That's it. And now this is your Weissner source. So ultimately, after doing all this, I am skipping 1 or 2 steps, and then I'll come back to what you asked. The total zoo recursion relation will be, because here there is a sum also, k not equals to 0, because I have kept the 0 mode aside. But here also there is a sum. The total endpoint function p n1 Zn can be written as trace 0 mode of the first object, which is a1 0, and other function which is there. So this is again n minus 1 point function with a 0 mode insertion, plus you will have j equals to 2 and then you have y plus m set j string, and then you have a2 to b of a1 m actual a j. So now, as you can see that the n point function is a sum over n minus 1 point function, and there is a n minus 1 point function with 1 0 mode insertion. That's why if you you can solve this recursively. Now, since I have bored you so much, I'll give you some one simple example. So let us compute. I have time, right?
What is that if?
Oh, sorry, this is phase. So I'll show you how to compute TT code. This is the simplest possible. The first term is just the 0 mode, which is L0 minus C by 24. Trace over 0 minus C by 24. And then one field is there, so TU2. And then you have Q to the power 0. This one. Plus you have now I should write half of the thing. So I don't need k equals to sum because this is just 2 point. Pt, then I have p in that j 1, and then I have trace of square mode of t acting on t d2. This term is simple because this is L0 minus C by 24. I can just write this as Q del Q of E into and this term, that's why I kept the P,
Yes, sir.
trace of that. Sorry. This term, that's why I kept the OP. So when I put m equals to 0, this is t0 on t, which I have said that anything acting on something is the m plus 1th pole in the OP. So if I put 0, that is the first order pole, u minus u1, that is t prime, and 1 point function of some total derivative is 0. So m equals to 0 does not contribute. M equals to 1 will contribute, that is 2t. And then m equals to 3, m equals to 3 will contribute, right? Because that's this c by 2. Now, this term, again, I will get another 0 mode of t equals to recursion delta. So this is just derivative, 2 times derivative on the character, plus for I will have p2 z2 by z1, and then some I'll have 2 t's because of m equals to 1. So again, I'll have trace of t, and I'll have c by 2, trace of nothing, character. P4.
What is it?
I mean, it's this character. Yeah. So, and then this is again, I can write as q del q of the character. And ultimately, you can do the normal ordering of this. And if you do the normal ordering, you'll see that you do normal ordering, pt, trace. Okay. You do normal ordering, you can write this as, and again skipping step. So d square plus c 1 0 1 e4. This is the error I'm on. And you can see that ET correlator is completely modular form. So weight 4 modular form also. And now what we can do is that
What's that factor?
each factor, sorry,
T by C, right?
1440.
Why you get 1440?
Oh, is the
That's the modular. I mean, is this the modular invariant?
this is without the fact that it's still modular invariant, right?
Yeah.
Because this is the modular invariant, this is a modular. And this is vector value modular form of it.
Yeah.
So everything is modular. This number is important because if you now, since you have the thermal correlator, remember at the beginning I've said that you do this, you take q to the power q tends to 0 limit and divide this.
Yeah.
And if you do this, because characters, the first term will come, if you do the q expansion of a character, you will just get first term is just 1, right? Because q tends to 0 limit. E4 is also 240 something. So ultimately, if you take q tends to 0 limit, you will get I hope I have written it somewhere.
I see. So
Okay. If you take q tends to 0 limit, you get delta square, or rather, I should say h square minus by 2 by 12 plus 5c plus 5c 5c plus 22. Again, you have EM problem. Wait, 0. And this is basically if you take the KV charge and you act on the highest rate state, you get this number, which has been independently PLC have computed using PDA and stuff like that. And on thermal correlator we verify. Okay. So I have time.
So formally, we will, in this, we will continue.
Okay.
Recording. Some people can have fit and.
Okay. Yeah.
And then you can continue.
Yeah. I can continue after 5 minutes.
Thanks. Thanks a lot.